They projected its dissipation. By this juncture, the celestial body designated 3I Atlas was expected to have receded beyond the sun's embrace, vanishing from our view and our thoughts. Yet, it did not. It persisted. And in this very act of defiance, a transformation occurred. Its luminescence, its velocity, its hushed presence. Consequently, on the 15th day of December 2025, our planet and 3I Atlas are poised for an alignment unprecedented in recorded epochs. Every optical instrument is trained upon it. Every transmission is under scrutiny, as it may very well execute an act for which humanity is utterly unprepared. Officially, NASA categorizes it as an innocuous cosmic sojourner. But what if the reality is that it is observing, awaiting a signal, or perhaps a propitious moment? Remain with me, for by the conclusion of this narrative, you will grasp why certain individuals posit that this juncture will not merely redefine astrophysics, but fundamentally alter us. The chronological reckoning is imminent and has already commenced. If this enigma has you on edge, much like it does me, do not remain in obscurity. Engage the like button and subscribe, for you will not wish to miss the unfolding events as this progresses in real time. Share your location, your current time, and your belief regarding the completeness of the information we receive about these earth-shattering discoveries in the comments section. And if you wish to contribute to the growth of this community, disseminate this video on X, Facebook, Reddit, or even within your personal group conversations. Your engagement is the catalyst that empowers us to continue pursuing narratives such as this. Therefore, our sincere gratitude for your unwavering support. Part 1. The countdown initiates. Envision this scenario. It is a clear evening in late October of the year 2025. You find yourself in your backyard, gazing skyward at the celestial tapestry. All appears tranquil, undisturbed. However, somewhere in the vast expanse, traversing at speeds far exceeding any man-made conveyance, an entity originating from beyond our solar system is hurtling towards an engagement that was never scheduled. The National Aeronautics and Space Administration reassures you not to be concerned. The European Space Agency characterizes the event as routine. They maintain that December the 15th will be an unremarkable day, but here lies what is omitted from their official communiques. Herein lies the source of sleepless nights for amateur astronomers, meticulously refreshing their telescope feeds, meticulously re-examining their calculations. There is an inherent characteristic of 3I Atlas that defies conventional behavior. To date, we have documented the passage of merely 3 interstellar objects through our cosmic vicinity. The inaugural instance was Oumuamua in 2017, that peculiar elongated visitor whose acceleration defied simple gravitational explanations, a subject of ongoing scientific debate. The subsequent encounter was Boris in 2019, exhibiting traits more akin to a typical comet, but nevertheless raising questions about its origin and composition. Now, we confront 3I Atlas, the third interstellar voyager, and it is deviating from the established script. On the first day of July in the year 2025, the Atlas telescope situated in Chile captured an anomalous anomaly in its observational imagery. A faint luminescence, discernible against the backdrop of stars. Within days, astronomers had computed its trajectory, realizing the significance of their observation. This object was not gravitationally tethered to our Sun. Its orbital path was hyperbolic, signifying its origin from the interstellar void and its eventual return thereto. The numerical data presented a startling revelation. This entity was traversing at an approximate velocity of 60 kilometers per second. Its eccentricity was measured within the range of 6.14 to 6.20, far surpassing the threshold separating celestial bodies bound to our solar system from those of interstellar origin. It was approaching with considerable speed and would depart with even greater velocity. NASA and ESA promptly disseminated the fundamental details. Perihelion, its closest proximity to the Sun, was projected to occur around October the 30th, at an approximate distance of 1.36 to 1.4 astronomical units. This places it within Earth's orbital plane, closer than Mars, yet still at a comfortably safe distance. Subsequently, 3I Atlas would execute a parabolic arc, achieving its closest approach to Earth in mid to late December, at an approximate distance of 1.8 astronomical units. This equates to roughly 168 million kilometers. Nothing to cause alarm, they asserted. Merely another transient visitor. However, a nascent discourse began to emerge on astronomical forms, within amateur observation circles, and in the comment sections of video presentations concerning the comet. Individuals started to share observations that did not precisely correlate with the official projections. One account claimed the object's positional coordinates were found to be offset by several arc minutes from the predicted location, as per JPL horizons. Another observer presented photometric data indicating luminosity fluctuations that deviated from conventional models of cometary activity. A third noted an unexpected orientation of the comet's tail, suggesting it was being influenced by forces not accounted for in the prevailing models. Are these observations veridical, or are they artifacts of calibration, inaccuracies, atmospheric disturbances, or perhaps wishful interpretations? This is the critical inquiry. Because if 3I Atlas is indeed deviating, even minutely, from its predicted trajectory, then our current understanding of its December passage may be fundamentally flawed. Furthermore, if these deviations are systematic and cumulative over time, then the geometrical configuration on December the 15th could diverge significantly from the orbital paths disseminated by official almanacs. Allow me to elucidate the celestial mechanics anticipated for December the 15th. By that specific date, 3I Atlas will have completed its perihelion passage more than 6 weeks prior. It will be receding from the Sun but still in relatively close proximity to Earth. Crucially, the planetary alignment will be nearly perfect. A direct line drawn from the Sun, passing through 3I Atlas, will point almost precisely towards Earth. Our planet will be situated downstream from the comet, within whatever atmospheric wake it generates. If 3I Atlas has developed a tail composed of ionized particles, if it has been expelling gas and dust heated by its close solar proximity, then Earth will find itself directly within the trajectory of this ejected material. At a distance of approximately 1.6 to 1.8 astronomical units. While substantial, this distance is still within the range where certain phenomena can propagate. Radio waves would traverse this expanse in approximately 8 to 9 minutes. Charged particles, carried by the solar wind, could drift across this void within days to weeks. Even gravitational influences, while infinitesimally subtle, would be technically detectable. Therefore, we must confront the unspoken question: what if December the 15th is not devoid of consequence? What if this celestial alignment precipitates an unforeseen event? I am not alluding to a direct impact. 3I Atlas is far too distant for such an occurrence. I am referring to something more subtle. A localized electromagnetic surge, an emission of radio frequencies, a sudden fluctuation in luminosity, a disruption in our satellite network, or an inexplicable aurora appearing at latitudes where such phenomena are typically absent. Something subtle enough to be dismissed as coincidence, yet sufficiently peculiar to provoke contemplation. The official narrative is unequivocal and confident. 3I Atlas presents no threat. Its trajectory is thoroughly understood. The object is merely a comet, albeit one originating from an extrasolar system. December the 15th will arrive and depart without incident. However, confidence and certainty are distinct. And in the silent intervals between official statements and public declarations, space exists for doubt. Space exists for questions. space exists for the possibility that we are on the precipice of witnessing something unprecedented, perhaps without even realizing it. Part 2, the entity that defies established norms. The officially recognized discovery date is July 1st, 2025, but the saga of 3I Atlas actually commenced at an earlier stage, significantly so. Upon reviewing archived data from the Hubble Space Telescope, researchers unearthed an unexpected finding. The comet was already exhibiting activity, generating a discernible coma of gas and dust while still situated at a distance of approximately 6.5 astronomical units from the Sun, a position beyond Jupiter's orbit. Comets are not anticipated to behave in such a manner. The prevailing scientific model posits that they remain inert and frozen until they approach sufficiently close to the Sun for solar radiation to initiate the sublimation of their icy components. However, 3I Atlas was already energized, already shedding matter, while still within the frigid outer reaches of our solar system. This pre-discovery activity imparts crucial information. This entity is anomalous. Either it is composed of unusually volatile substances that sublimate at lower temperatures than standard comets, or it possesses an internal thermal source that eludes our comprehension, or it is not entirely a naturally occurring phenomenon. These are the prevailing hypotheses, each carrying significant implications. Let us examine the pertinent numerical data. Observations conducted by the Hubble Space Telescope have established certain parameters regarding the dimensions of 3I Atlas. The nucleus, the solid core of the comet, is estimated to be between 0.444 kilometers and 5.6 kilometers in diameter. This represents a substantial range of uncertainty. It could be a comparatively modest aggregate of ice and rock, or it could be considerably larger. The size is significant as it dictates the quantity of material the comet can release, the magnitude of its gravitational pull, and the potential energy it might contain if an internal source is generating heat. The Gemini Observatory monitored 3I Atlas throughout its perihelion passage, corroborating the findings of the Atlas telescope, the hyperbolic trajectory, and the extreme velocity. However, Gemini also provided novel insights, polarimetric data. When light reflects from the comet's coma, it becomes polarized in a manner contingent upon the size and composition of the constituent dust particles. 3I Atlas exhibited an unusual characteristic: extreme negative polarization. This signature is indicative of dust grains possessing unconventional optical properties, or a composition that deviates from any known comets within our solar system. Now, we arrive at the aspect generating considerable conjecture: the observations made by amateur astronomers. Citizen scientists equipped with backyard telescopes and CCD cameras who meticulously track objects like 3I Atlas and disseminate their findings online. Commencing in October, a segment of these observers began reporting discrepancies. One group asserted that their measurements of the comet's right ascension and declination coordinates revealed offsets of several arc minutes relative to the predicted ephemeris. Another reported luminosity curves that did not align with the anticipated decline as the comet receded from the Sun. A third noted variations in the tail structure, suggesting non-gravitational accelerations. This is where the situation becomes intricate. While amateur observations are invaluable, they are also susceptible to errors. Atmospheric refraction can distort light and alter perceived positions. Calibration inaccuracies can compromise photometric readings. Telescope tracking errors can generate spurious motion. Consequently, when an observation reports an arc-minute offset, we are compelled to question its authenticity versus it being merely noise. The official ephemeris derived from JPL horizons incorporates intervals of uncertainty. Minor deviations are anticipated and considered normal. But what if these deviations are not minor? What if they are systematic and escalating? Let us perform a calculation. An arc minute represents 1/60th of a degree. At a distance of 1.8 astronomical units, a 1 arc minute angular displacement corresponds to a lateral deviation of approximately 780 kilometers. This is not an insignificant distance. If 3I Atlas is truly 780 kilometers off its projected course, this indicates a substantial, unmodeled acceleration. Over a period of weeks, a minuscule continuous acceleration could accumulate to precisely this magnitude of displacement. What could be the causative factor for such an acceleration? The most probable explanation is asymmetric outgassing. When ice sublimates on one hemisphere of the comet's nucleus, it generates a jet that propels the nucleus in the opposing direction. This is a recognized phenomenon observed in numerous comets. However, the magnitude is critical. For 3I Atlas to exhibit a deviation of hundreds of kilometers, the outgassing would need to be exceptionally vigorous or exceptionally unidirectional. In such a scenario, the comet would be demonstrably more active, more volatile, and more unpredictable than the prevailing models presuppose. Alternatively, another possibility exists. What if these deviations are not attributable to outgassing at all? What if an alternative factor is at play? An interaction with the solar wind's plasma, a gravitational perturbation from an unobserved mass, or perhaps even a form of propulsion? Yes, I have articulated the notion. The concept may appear preposterous, yet Oumuamua has demonstrated that seemingly absurd ideas can sometimes warrant serious consideration. When an object's behavior deviates from established physical laws, one is presented with two possibilities. Either our understanding of physics is incomplete, or the object itself is not what we initially perceive it to be. NASA's official stance remains unaltered. 3I Atlas is classified as a comet. Its trajectory is understood. The approach towards Earth in December poses no inherent risk. However, there are unspoken aspects. They are not issuing daily updates regarding the object's position. They are not releasing detailed photometric analyses. They are not addressing the amateur observations that purport to detect anomalies. This reticence could signify nothing. It could indicate that their resources are allocated to other priorities. Or it could suggest they are adopting a wait-and-see approach, observing whether these anomalies resolve themselves before issuing any public declarations. December the 15th is approaching. Whether we are prepared or not, the celestial configuration is fixed. Earth will be in alignment with the Sun and 3I Atlas. We will be positioned downstream of its tail, directly within the path of whatever material it has been expelling since its perihelion. If the amateur observations prove accurate, if the deviations are indeed real, then the object might be closer than anticipated or oriented differently than predicted. In such a case, the alignment could be more precise, more critical, and more significant than currently acknowledged. The fundamental question is not whether an event will occur. The question is whether we will recognize it when it transpires. Part 3. The mechanics of convergence. Visualize a clock. The Sun occupies the central position, with the planets tracing their orbits like hands sweeping across the dial. Now, imagine an uninvited guest, a fragment of interstellar debris that disregards our systematic, celestial clockwork, traversing the face of the dial at an oblique angle, moving with a velocity exceeding that of any object gravitationally bound to the Sun. Such is the nature of 3I Atlas. And on December the 15th, 2025, the clock's hands will align in a manner conducive to an unusual occurrence. Permit me to be precise regarding the geometry. Perihelion, the closest approach to the Sun, occurred around October the 30th, at an approximate distance of 1.36 astronomical units, roughly 204 million kilometers. This proximity was sufficient to intensely heat the nucleus through solar radiation, vaporizing ices, releasing gases, and thereby generating the coma and tail that render comets visible. For several weeks subsequent to perihelion, the comet has been progressing outward, ascending the gravitational gradient and charting a course towards eventual escape from the solar system. By December the 15th, 3I Atlas will be situated at an approximate distance of 1.6 to 1.8 astronomical units from both the Sun and Earth. However, distance is not the sole determinant. The crucial factor is alignment. On that specific date, a hypothetical straight line drawn from the Sun through the comet will point almost directly at Earth. We will not merely be in proximity, we will be downstream. We will be within the region where the comet's tail is expected to be. Comet tails are categorized into two types. Dust tails are composed of microscopic particles propelled outward by solar radiation pressure, exhibiting a gentle curvature that follows the comet's orbital path. Ion tails, conversely, consist of charged particles ionized by ultraviolet radiation from the Sun, pointing directly away from the Sun, driven by the solar wind. If 3I Atlas possesses an active ion tail, and if that tail is correctly oriented, then on December the 15th, Earth will traverse through it. While 1.6 astronomical units may seem like a considerable spatial separation, it is indeed substantial, approximately 240 million kilometers. However, consider the phenomena capable of propagating across such a distance. Radio waves travel at the speed of light, covering this gap in approximately 13 minutes. Charged particles within the solar wind move at speeds of several hundred kilometers per second, requiring days to weeks to traverse from the comet to Earth. Even comparatively slow-moving dust particles, if sufficiently small and electrically charged, can be influenced by electromagnetic forces. The pertinent question is not whether any material from 3I Atlas can reach us. The question concerns what specifically will arrive and what impact it will have upon its arrival. Let us address the concept of coupling. This is the scientific term denoting the interaction and energy exchange between two systems. Earth possesses a magnetosphere, a protective envelope of magnetic fields that shields us from the majority of charged particle radiation emanating from the Sun. When this radiation encounters the magnetosphere, it can induce disturbances. Magnetic field lines undergo reconnection. Electric currents are generated in the upper atmosphere. These phenomena manifest as auroras and can result in geomagnetic storms that disrupt satellite operations and power grids. Now, imagine that instead of the customary solar wind, the magnetosphere encounters a stream of ionized particles originating from a comet's tail. Would the interaction differ? Would the coupling be more intense or less so? Would we observe effects that deviate from conventional patterns? The distances involved are considerable. At 1.6 astronomical units, the density of the solar wind is significantly attenuated compared to its intensity near Earth. The magnetic field carried by the solar wind is also diminished. However, a comet's ion tail can contain its own unique magnetic structures, twisted filaments, and loops formed by the interplay between the outflowing gas and the interplanetary magnetic field. If Earth's magnetosphere were to intersect one of these structures, even momentarily, it could trigger localized disturbances, resulting in auroras at atypical latitudes, radio communication blackouts, or anomalies in satellite telemetry. These effects would not be catastrophic, nor would they typically warrant headline coverage. However, they would be sufficient to attract attention and provoke inquiry. An alternative hypothesis exists. What if the alignment transcends mere geometrical configuration? What if it pertains to temporal synchronization? Suppose that a particular event, triggered by 3I Atlas's passage through perihelion, such as a release of stored energy, a surge of activity, or a fundamental alteration in the object's behavior, occurred. And suppose that this event produced a phenomenon that propagates outward at a specific velocity, timed to arrive at Earth's location precisely on December the 15th. I must concede that this is purely speculative. However, it is speculation rooted in physical principles. If an object emits electromagnetic radiation, it travels at the speed of light. If it expels particles, they will travel at the velocity imparted to them. If it generates a disturbance in the interplanetary medium, that disturbance will propagate as a wave. The timing could be coincidental, or it could be intentional. This is the point at which mainstream scientists tend to disengage, expressing skepticism. They will assert that there is no known mechanism by which a comet could produce a targeted effect. They will argue that any energy release would be isotropic, dispersing in all directions, rather than focusing on Earth. They will maintain that the observed alignment is merely a geometric coincidence, a pattern that humans are imposing significance upon, and they are, most likely, correct. However, a nagging thought persists. We have never before witnessed an interstellar comet traverse our solar system during the era of modern astronomical observation. Oumuamua was the first, yet it lacked a discernible tail. Boris was the second, but its geometric trajectory differed. 3I Atlas presents us with an unprecedented scenario, a situation for which we have no prior empirical data. An interstellar visitor possessing an active coma and tail, passing sufficiently close to interact with Earth's magnetosphere, and aligned in such a manner as to place us directly within its outflow path. While we possess models and predictive algorithms, it is imperative to remember that models are only as robust as the data upon which they are constructed. And for this specific context, we lack the requisite data. December the 15th represents a test, not a test that we devised or solicited, but a test nonetheless. If no significant event occurs, our existing models will be validated, and the skeptics will be vindicated. Conversely, if an event transpires, even a minor one, it will signify that our comprehension of cometary interactions was incomplete. In either outcome, valuable insights will be gained. Nevertheless, I cannot help but ponder which revelation would be more profoundly unsettling: the confirmation of our complete understanding, or the disclosure that we have been overlooking something significant all along. Part 4. 5 scenarios that nobody wishes to contemplate. I intend to present 5 distinct hypotheses. 5 theoretical scenarios that could, in principle, yield observable effects on December the 15th. It is crucial to preface this by stating that none of these hypotheses represent conventional scientific predictions. They are, in essence, thought experiments. They are the types of ideas that are typically discussed in hushed tones during informal discussions, following conference sessions, or debated late at night on online forums by individuals who relish pushing the boundaries of conventional thought. However, they warrant examination, as even the most speculative hypothesis can offer valuable insights into the realm of possibility and impossibility. Scenario 1. The quiescent activation event. The underlying premise is as follows. The celestial body known as 3 Atlas has traversed the vastness of interstellar space, remaining in a state of cold dormancy for countless millennia. Its journey brings it into our solar system, drawing nearer to the sun, and for the very first time in its extensive existence, it begins to warm. This thermal stimulation appears to awaken something within. Perhaps it's a molecular process deep within its core, or it could be the evaporation of a volatile substance that was stable in the frigid void, but brittle under solar radiation. It's even conceivable that it's an entirely unknown energy reservoir, a form of power for which we lack a designation. Regardless of its nature, this activation initiates a perihelion effect. This activation, in turn, generates an output, a directed surge of electromagnetic energy, a dispersion of particles, or a combination thereof, propagating outwards as either a focused beam or an expanding wave. Should the timing and spatial orientation be precisely aligned, this output would reach Earth on December 15th. What would our observations reveal? The outcome hinges on the characteristic of this output. If it manifests as radio waves, we would perceive a brief, fleeting signal, potentially on frequencies we aren't actively monitoring. should it be high-energy particles, our cosmic ray detectors and satellite radiation monitors would register a significant increase. In the event of an electromagnetic pulse, we might witness transient interruptions in communication networks or power grids. While none of these possibilities portend ultimate disaster, they would undoubtedly be discernible and defy conventional scientific explanations. Scenario 2 explores gravitational and plasma resonance. This hypothesis is more nuanced. The premise is that the planetary alignment occurring on December 15th establishes a unique configuration wherein Earth's magnetosphere becomes acutely susceptible to disruptions within the interplanetary medium. This phenomenon is analogous to resonance in a musical instrument. Striking the correct frequency causes the entire structure to vibrate. Typically, Earth's magnetosphere is resilient and provides robust protection. However, under specific circumstances, such as when the solar wind possesses a particular velocity and magnetic orientation, even minor disturbances can elicit a substantial reaction. Now, let us consider the possibility that the ion tail of 3 Atlas carries its own embedded magnetic structures. If these structures interact with Earth's magnetic field in a manner that triggers this resonant point, the consequence would be an amplified geomagnetic response. Auroral displays would extend to latitudes not normally experiencing them. Ground-based magnetometers would record unusual fluctuations. Satellites in certain orbital paths might experience increased atmospheric drag or electronic interference. Again, this scenario does not suggest apocalyptic consequences, but rather effects substantial enough to be recorded in scientific data and to prompt profound questions among researchers regarding the underlying cause. Scenario 3 posits fragmentation and an outgassing burst. Comets are inherently fragile entities, not solid rocky bodies, but rather aggregations of ice and dust, bound by weak gravitational forces and even weaker cohesive bonds. Occasionally, they disintegrate, particularly after a close solar passage, when thermal stresses fracture the nucleus. If 3 Atlas were to fragment near its perihelion, the resultant pieces would continue along slightly divergent trajectories. Some of these fragments might expel gas and dust more vigorously than the primary nucleus, creating temporary enhancements in the surrounding coma. Should one of these bursts coincide precisely with the geometric alignment on December 15th, Earth could traverse a denser than anticipated cloud of cometary detritus. Satellites in low Earth orbit would encounter heightened atmospheric drag. We might observe an increase in meteor sightings as dust particles incinerate within the upper atmosphere. Optical telescopes could detect a sudden surge in brightness or an alteration in the tail's structure. This effect would be transient, lasting for mere hours, perhaps a few days. However, within that brief interval, 3 Atlas would exhibit behavior inconsistent with current predictive models. Scenario 4, the probe hypothesis, ventures into speculative territory, acknowledged by many astronomers only in private. To explore this, we must entertain the notion that 3 Atlas is not entirely a natural phenomenon. Imagine that its icy nucleus harbors something artificial, a probe, a communication relay, or a dormant mechanism that has been drifting through space for eons, awaiting the opportune moment to activate. Its size is not necessarily a limiting factor. A device equivalent to a car, embedded within a comet nucleus, several kilometers in diameter, would remain undetectable by our telescopes. Furthermore, it wouldn't need to be continuously operational. It might activate upon sensing the proximity of a star, or it could harness solar radiation to replenish its energy reserves. It might deliberately wait for a specific geometric configuration, such as the alignment on December 15th, before transmitting a signal, a beacon, a data packet directed towards a particular cosmic destination. If Earth happens to lie within the transmission's path, we would intercept this signal. It could be at radio frequencies, optical wavelengths, or an entirely different spectrum. Its modulation might be distinct from background noise, or it could be subtle, detectable only through dedicated observation. Researchers involved in the search for extraterrestrial intelligence, SETI, harbor hopes for scenarios precisely like this. A technological signature delivered directly to us by a cosmic wanderer. While representing an extreme long shot, it is not physically implausible. Scenario 5, the optical reflection phenomenon, is comparatively mundane, but warrants mention. Consider the possibility that on December 15th, the angle formed by the Sun, 3 Atlas, and Earth reaches a critical value that maximizes the reflection of sunlight off the comet's coma. Visualize it as a brilliant glint, akin to sunlight reflecting off an airplane's fuselage at a precise angle, producing a dazzling flash. If the dust particles within the coma possess the appropriate size and composition, and are arranged in a specific formation, the comet could momentarily increase in brightness by several magnitudes for a period of a few hours. Observers on Earth would witness a temporary enhancement in luminosity. Social media platforms would likely be inundated with reports of an unusual celestial glow. Amateur astronomers would eagerly attempt to capture images, after which the phenomenon would recede as the geometric alignment shifted, restoring the comet to its normal brightness. This event would be devoid of danger, yet it would possess an eerie, unsettling quality, fostering a sense that the universe is conveying a message, even if it is merely an illusion created by the interplay of light and physics. These 5 distinct scenarios encompass a spectrum from established scientific principles to highly speculative conjectures. Their common thread is their theoretical possibility. The likelihood of each varies considerably. Some are vanishingly improbable, while others are merely unlikely. Crucially, none contravene the fundamental laws of nature. This inherent possibility is what imbues December 15th with such significance. It is not an expectation of any particular outcome, but rather the absence of absolute certainty that makes the date compelling. In the space between expectation and definitive knowledge, there exists fertile ground for unforeseen events. Part 5 delves into the architecture of institutional silence. NASA's official pronouncement regarding 3 Atlas is concise and confident. The object poses no threat to Earth. Its trajectory is well understood, and its December approach is a routine event that will be monitored through standard observational procedures. The implied message is one of reassurance, suggesting nothing extraordinary is occurring. While this assessment may be accurate, the management of information surrounding 3 Atlas exhibits a curious pattern that merits attention. Let us begin with fundamental observations. Upon its discovery in 2017, it took several weeks for the scientific community to confirm its interstellar origin. Initial observations suggested it was a typical asteroid. It was only through detailed orbital calculations that astronomers definitively identified it as an object originating from beyond our solar system. The subsequent announcement generated immense public fascination, leading to widespread media coverage, documentary productions, and even congressional inquiries, all seeking to understand the nature and provenance of Oumuamua. In contrast, the information dissemination regarding 3 Atlas has followed a different trajectory. Its interstellar nature was recognized almost immediately. While the initial discovery announcement noted its hyperbolic orbit, the subsequent flow of information significantly diminished. There have been no major press conferences, no detailed scientific papers published in prominent journals, and no follow-up observations made publicly available. The object is undoubtedly being tracked, and data is being collected. But this process lacks the transparency that characterized the Oumuamua situation. Why this disparity? One plausible explanation is that 3 Atlas possesses less scientific intrigue compared to Oumuamua. It appears to be a comet, albeit one from another star system. Comets are commonplace phenomena, and we have extensive records of studying hundreds of them. Thus, There may be little new or groundbreaking information to impart. However, this rationale does not entirely align with the observed facts. The pre-discovery activity observed at significant heliocentric distances is unusual. The extremely negative polarization is noteworthy. Reports from amateur observers regarding trajectory and brightness anomalies are also peculiar. There is, demonstrably, a wealth of scientifically interesting aspects to 3 Atlas. So, why the reticence? Another consideration is caution. Space agencies learned from the Oumuamua event that premature disclosure of surprising findings can precipitate an uncontrollable media frenzy. Recall how swiftly Oumuamua transitioned from an astronomical curiosity to a potential alien probe in the public consciousness. NASA might be intentionally downplaying 3 Atlas to avert a recurrence of such sensationalism. A more prudent approach would be to await the completion of data analysis and the establishment of a definitive interpretation before issuing any statements that could be misconstrued or sensationalized. Nevertheless, a third possibility, one that is more difficult to disregard, exists. What if the silence is not a product of caution or a lack of interest, but rather a reflection of uncertainty? What if NASA and the European Space Agency, ESA, are encountering data that they cannot readily comprehend and are hesitant to discuss until a more satisfactory explanation emerges? Institutional science inherently prioritizes risk aversion. Announcing an anomaly prior to a comprehensive explanation can have detrimental career consequences. It is considerably safer to maintain silence, conduct further observations, meticulously re-verify calculations, and only then present findings publicly once a complete narrative is established. Now, let us address protocols. The International Academy of Astronautics has established guidelines, known as the Post-Detection Communication Protocols, for managing potential technosignatures. These protocols delineate the necessary steps to be undertaken upon the detection of a signal that might originate from an extraterrestrial source. Key components include verification, consultation with peer experts, and eventual public dissemination. However, a built-in delay mechanism exists within these protocols. They emphasize that no announcement should be made until the detection is unequivocally confirmed and its implications are fully understood. Has 3 Atlas triggered any of these protocols? The extent of this is unknown. The protocols are primarily designed for radio signals and intentional transmissions, rather than for the ambiguous behavior of a comet-like object. Nevertheless, some observers have speculated that the unusual characteristics of 3 Atlas may have prompted informal consultations among SETI researchers and planetary defense specialists. If even a remote possibility exists that the object is artificial or carries some form of signal, such discussions would likely be occurring behind closed doors. The Planetary Defense Coordination Office, a division within NASA's Office of Planetary Defense, maintains a registry of celestial objects requiring heightened monitoring. This includes near-Earth asteroids exhibiting uncertain trajectories or peculiar attributes. While 3 Atlas is not technically classified as a near-Earth object, as it is not gravitationally bound to our solar system, certain online forum discussions have claimed its temporary inclusion on internal watch lists utilized for training exercises or protocol development. These assertions remain unverified, and NASA has neither confirmed nor denied them. However, if true, it would suggest that individuals within the scientific establishment considered 3 Atlas worthy of exceptional attention. This is where the role of psychology becomes relevant. Humans are inherently inclined to seek patterns and ascribe meaning, often even in the absence of genuine connections. When an institution chooses to remain silent, speculation inevitably fills the void. The lack of information can be interpreted as evidence of concealment. This is the genesis of conspiracy theories, not necessarily born of malevolence, but from the disparity between our desire for knowledge and the information we are provided. December 15th has become a focal point for online discourse precisely because it represents a specific, tangible moment in time. If one subscribes to the notion that something unusual is transpiring with 3 Atlas, a temporal marker is essential. December 15th provides this critical element. It is sufficiently proximate to evoke a sense of anticipation, sufficiently precise to facilitate predictions and preparations, and sufficiently aligned with celestial geometry to lend an air of plausibility. Whether any extraordinary event actually unfolds on that date is almost secondary. The date itself has acquired significance through its repeated invocation across various contexts. My intention is not to assert whether NASA is withholding information, as I lack such knowledge. However, I can affirm that the very structure of institutional silence cultivates an environment where doubt flourishes. Each unanswered question serves as a catalyst for suspicion. Every delay in data release is perceived as potential evidence of a cover-up, and every reassurance that no cause for concern exists paradoxically reinforces the belief that something is indeed amiss. This dynamic is currently unfolding in real time as December 15th approaches. The silence persists, the questions remain unaddressed, and the countdown continues. Part 6 draws lessons from previous celestial visitors. In October of 2017, a telescope at the University of Hawaii, engaged in scanning for near-Earth asteroids, detected an anomaly, an object moving with such velocity and along such an inclined trajectory that its presence could not be attributed to our sun's gravitational influence. The discovery team christened it Oumuamua, a Hawaiian term signifying scout or messenger, a name that would prove remarkably prescient. Oumuamua was unlike any celestial body previously observed. Its inferred shape was highly elongated, perhaps 10 times longer than its width. It exhibited no discernible coma or tail, suggesting it was not a comet in the conventional sense. However, as telescopes tracked its progress over the subsequent weeks, a puzzling observation emerged. The object was accelerating. This acceleration was subtle, a slight additional impetus beyond what solar gravity alone would dictate. This non-gravitational acceleration became the central enigma surrounding Oumuamua. Scientists proposed a variety of explanations. One possibility was that it was indeed outgassing, but so feebly that its coma remained undetectable. Another hypothesis suggested radiation pressure. The effect of sunlight impinging on its surface was providing the extra push. A combination of both was also considered. Yet, none of these explanations perfectly reconciled with the observed data. The acceleration seemed too significant to be solely attributed to radiation pressure unless the object possessed an exceptionally low mass and thin structure. The absence of a visible coma made the outgassing theory problematic. Consequently, a period of intense debate ensued. Some researchers, including Harvard astronomer Avi Loeb, posited that Oumuamua might be artificial in origin, perhaps a light sail, a probe, or some other constructed artifact, rather than a naturally formed body. The broader scientific community largely dismissed this notion, adhering to the principle that extraordinary claims necessitate extraordinary evidence, and the evidence supporting Oumuamua's artificiality was deemed insufficient. However, this controversy imparted a crucial lesson. When an object behaves in ways that defy our expectations, we must remain open to considering unconventional explanations. While not the initial recourse, these possibilities should be retained as viable considerations when conventional explanations prove inadequate. 2 years later, in August of 2019, amateur astronomer Gennady Boris discovered a second interstellar visitor using a telescope he had constructed himself. This object was unequivocally a comet, displaying a prominent coma and tail. Spectroscopic analysis indicated its composition was similar to comets originating from our own solar system. Borisov, in many respects, conformed to what scientists anticipated an interstellar comet would resemble, which was reassuring. It suggested that Oumuamua might have been an anomaly, an exceptional case, rather than an indication that our understanding of interstellar objects was fundamentally flawed. However, even Borisov presented its own set of surprises. Its ratio of carbon monoxide to water differed from that of typical solar system comets. Its nucleus fragmented as it approached the Sun, dispersing into multiple fragments along its orbital path. And similar to Oumuamua, it exhibited non-gravitational acceleration, attributed to outgassing, although in Borisov's case, the mechanism was clearly understood and uncontroversial. Now, we have 3 Atlas, the third interstellar visitor. What insights does it offer? Firstly, it underscores the diversity of these objects. Oumuamua lacked a visible coma, while Borisov possessed a pronounced one. 3 Atlas displays extreme polarization and unusual dust characteristics. Each object is distinct, challenging our assumptions in its own unique manner. Secondly, it reinforces the observation that non-gravitational accelerations are common among interstellar objects. Both Oumuamua and Borisov exhibited this phenomenon. If amateur observations suggesting 3 Atlas is also deviating from its predicted trajectory are accurate, this would mark a consistent pattern across all 3 instances. Thirdly, it highlights our improving capabilities in detection and characterization. We discovered Oumuamua only after it had already passed its closest point to the Sun and was receding from the solar system. We identified Borisov several months prior to its perihelion, affording us more time for study. We detected 3 Atlas even earlier, with pre-discovery observations extending back to when it was still distant from the Sun. This progression is significant. Each interstellar object we identify enhances our knowledge of what lies beyond and refines our methods of study. Concurrently, it reveals the vastness of our remaining ignorance. Prior to 2017, we possessed theoretical frameworks for interstellar objects, but lacked direct observational data. Now, we have 3 examples, each raising as many questions as it answers. How prevalent are objects like Oumuamua? From where do they originate? How long do they traverse interstellar space before encountering a star? Are there objects extant that are even more extraordinary than those we have encountered thus far? The history of these 3 visitors also illuminates patterns in the responses of both the scientific community and the public. With Oumuamua, initial excitement was followed by intensive scrutiny and subsequent controversy. With Borisov, there was considerable interest but less dramatic fervor, as it aligned more closely with existing expectations. With 3 Atlas, we are still in the nascent stages. Data remains incomplete, and interpretations are preliminary. However, the seeds of controversy are already being sown by amateur observations and trajectory anomalies. If December 15th passes without incident, 3 Atlas will likely join Borisov in the classification of interesting but not shocking. Should something unexpected occur, even if minor, it could ascend to the status of Oumuamua, becoming a source of prolonged debate and speculation for years to come. There is a lesson to be gleaned from this entire episode concerning humility. Each of these objects has served as a reminder that the universe is under no obligation to conform to our theoretical constructs. We formulate theories based on the available data, but the data we possess is invariably incomplete. Interstellar objects spend millions or billions of years traversing the void between stars. They experience environments and conditions that we can scarcely replicate in laboratory settings. Upon their arrival in our solar system, they carry with them information about processes and compositions that may be rare or entirely absent in objects formed within our own system. The pertinent question is not whether 3 Atlas will surprise us, but rather whether we are prepared for such surprises. Do we possess the necessary instrumentation, funding, focused attention, and intellectual agility to recognize truly novel phenomena when they appear? Oumuamua eluded us before we could acquire a thorough understanding. Borisov afforded us more time but still left unanswered questions. 3 Atlas remains within our observational reach, continuing its approach towards its moment of closest alignment. This presents us with an opportunity. Whether we utilize it judiciously remains to be seen. Part 7 explores the phenomenon of amateur observers, detecting phenomena that professionals may overlook. A subtle revolution is underway in the field of astronomy. It is not driven by colossal space telescopes or governmental agencies, but by individuals equipped with backyard observatories, modified digital cameras, and an unyielding passion for celestial observation. These amateur astronomers are not career scientists. They do not hold doctoral degrees or secure research grants. However, they possess something equally valuable: time, unwavering dedication, and freedom from the bureaucratic constraints that often characterize institutional research. When the announcement of 3I Atlas surfaced in July of 2025, the amateur astronomical community sprang into action without delay. Within a mere handful of days, skywatchers scattered across the globe were meticulously charting the comet's path, meticulously documenting its celestial position, diligently measuring its luminosity, and capturing detailed images of its ethereal coma and tail. While some employed highly sophisticated instruments, others utilized comparatively rudimentary setups. Nevertheless, every single one of them generously contributed their observational data to online forums and publicly accessible databases, making their findings available to anyone interested. It was precisely at this juncture that the puzzling discrepancies began to emerge. Allow me to elucidate the methodology behind determining the precise location of celestial bodies. When you capture an image of an object in space, you are essentially recording its placement against the backdrop of fixed stars. Provided you possess the exact coordinates of these reference stars, you can then accurately calculate the coordinates of your intended target. This specific astronomical technique is known as astrometry. Although it might sound straightforward, this process is inherently fraught with potential sources of error. Your telescope, for instance, might not be perfectly aligned with the celestial sphere. The Earth's atmosphere could be causing the refraction of light, bending its path. Furthermore, the sensor within your camera might exhibit inherent distortions. Any of these contributing factors can introduce inaccuracies ranging from several arc seconds to even entire arc minutes. Professional astronomical observatories meticulously compensate for these potential errors through rigorous calibration procedures. They rely on comprehensive reference catalogs that detail star positions measured with extraordinary precision, down to the millisecond level. They employ sophisticated models, taking into account atmospheric temperature and pressure, to correct for light refraction. To mitigate the impact of random fluctuations, they average multiple observations. The ultimate outcome of these meticulous efforts is positional data accurate to within a fraction of an arc second. Generally speaking, amateur observers cannot attain this elevated level of accuracy. Their typical margin of error is considerably larger, often falling within the range of 5 to 10 arc seconds. Consequently, when an amateur observer reports that 3I Atlas is displaced from its predicted location by several arc minutes, we are compelled to question whether this deviation is a genuine astronomical phenomenon or merely a consequence of measurement imprecision. 1 arc minute is equivalent to 60 arc seconds, which is 10 times greater than the typical uncertainty associated with amateur observations. It is therefore exceedingly difficult to attribute an arc-minute displacement solely to measurement error, unless, of course, a significant flaw occurred during the observation itself. Conversely, explaining such a substantial offset as a true orbital deviation presents its own challenges, implying that the comet is experiencing extraordinarily potent, non-gravitational forces. This is precisely where the situation becomes truly intriguing. An assortment of amateur observers, utilizing diverse equipment from various geographical locations, have independently reported analogous discrepancies. Not identical, mind you, but exhibiting a clear correlation. They are consistently observing the comet positioned in the same general direction relative to the predicted ephemeris. This pervasive correlation renders it substantially more difficult to dismiss as mere random error. When independent measurements converge, even if they contain some degree of noise, it strongly suggests that they are capturing an authentic underlying phenomenon. The crucial question then becomes, what exactly are they observing? One plausible explanation is that the ephemeris itself may be inaccurate. The official predictions, emanating from the Jet Propulsion Laboratory's Horizon system, are derived from orbital elements established during the comet's early observational phase, when it was still situated at a considerable distance from the Sun. If those initial measurements contained subtle inaccuracies, or if the orbital calculations failed to adequately account for non-gravitational accelerations, the predicted position could gradually diverge from the comet's true trajectory over time. By the month of December, such accumulated error could have become quite significant. Another compelling possibility is that 3I Atlas is indeed undergoing non-gravitational accelerations that were not incorporated into the initial orbital solution. Comets are notoriously prone to such unpredictable behavior. As they approach the Sun and their icy constituents sublimate, they generate jets of material that exert propulsive forces on the nucleus in unanticipated directions. While this effect is typically minor, it can accumulate substantially over extended periods. In the case of a highly active comet, such as 3I Atlas appears to be, these accelerations could be sufficiently pronounced to induce detectable deviations in its path. Let us engage in some quantitative analysis. Suppose 3I Atlas experiences a non-gravitational acceleration equivalent to 10 to the power of -5 meters per second squared. This represents an exceedingly minute acceleration, approximately 1/millionth of Earth's surface gravity. Over the span of a single month, such an acceleration would alter the comet's velocity by roughly 26 meters per second. Extending this period to 2 months, from perihelion until December 15th, the velocity change would increase to approximately 52 meters per second. This resultant change in velocity directly translates into a displacement in the comet's position. Employing fundamental principles of kinematics, an acceleration of 10 to the power of -5 meters per second, squared acting over a duration of 60 days, would result in a displacement of approximately 1,500,000 kilometers. At the considerable distance of 3I Atlas, this extensive physical displacement corresponds to an angular offset of roughly 5 arc minutes. Therefore, a deviation on the scale of arc minutes is indeed a plausible consequence if the comet is subjected to moderate non-gravitational acceleration. The critical question that remains is whether this particular acceleration has been factored into the official orbital solution. If it has, then the observations made by amateur astronomers must either be flawed or indicative of phenomena extending beyond typical cometary behavior. Conversely, if it has not been accounted for, then the Jet Propulsion Laboratory will need to revise their ephemeris by incorporating more refined force models. Now, let us shift our focus to photometry, the process of measuring an object's brightness. Amateur observers have been diligently tracking the luminosity of 3I Atlas since its initial discovery, and several of them assert that the observed light curve deviates from the predicted trajectory. Specifically, they report that the comet is diminishing in brightness more gradually than anticipated as it recedes from the Sun, or that it is exhibiting unexpected periods of intensification. Predicting the brightness of a comet is an undertaking notoriously fraught with complexity. It is contingent upon a multitude of factors, including the size of the nucleus, the quantity of dust and gas being expelled, the reflectivity of these ejected particles, and the specific geometric configuration of the observation. Professional models typically utilize empirical formulas that have been meticulously calibrated based on the study of past comets. However, each comet possesses its unique characteristics. Some adhere closely to these established formulas, while others diverge significantly. Consequently, a discrepancy between the predicted and observed brightness is not inherently a cause for alarm. It may simply signify that this particular comet is exhibiting a level of activity that is either above or below the average observed in prior comets. However, there lies a subtle but crucial nuance. If these brightness variations are systematic, if they manifest in discernible patterns that correlate with the comet's position or orientation, then this could point towards something truly noteworthy. For instance, if the comet experiences a surge in brightness whenever it is oriented in a specific direction relative to Earth, this might suggest a directional outburst of material or the presence of a reflective surface feature. Such granular details are precisely what can only be discerned through meticulous and continuous monitoring by a broad spectrum of observers. The collective amateur astronomy community is currently undertaking this very essential monitoring. They are diligently constructing light curves with a temporal resolution that ranges from nightly to, in some instances, even hourly intervals. They are actively exchanging notes, cross-referencing their measurements, engaging in spirited debates regarding interpretations, and crucially, they are conducting all of this openly within public forums and social media platforms, allowing anyone to follow their progress. This transparency serves as both a significant strength and, conversely, a potential weakness. It facilitates the rapid dissemination of information and fosters collaborative problem-solving. However, it also inadvertently provides an avenue for errors and misunderstandings to propagate with alarming speed. Therefore, this is our current standing. The observations contributed by amateur astronomers suggest the presence of anomalies, including positional offsets, fluctuations in brightness, and alterations in tail structure. While some of these findings might indeed represent genuine phenomena, others could be mere artifacts of the observational process. The paramount challenge lies in effectively distinguishing between the genuine signal and the pervasive noise. Professional astronomers possess the requisite tools and expertise to undertake this critical separation. However, it is often observed that they do not consistently pay adequate attention to the reports submitted by their amateur counterparts. A noticeable chasm exists between these two distinct communities, characterized by a disconnect in communication and a deficit of mutual trust. Amateurs often feel that their valuable data is being overlooked by professionals. Conversely, professionals sometimes perceive that amateurs are prematurely drawing conclusions without adhering to the stringent standards of proper calibration. The event scheduled for December 15th presents a unique opportunity to bridge this divide. Should the alignment induce any discernible effect, the amateur community will be keenly observing. They will meticulously record it, diligently measure it, and disseminate their findings instantaneously. Conversely, if no observable phenomenon occurs, they will meticulously document that outcome as well. Regardless of the eventual findings, their observations will invariably become an integral part of the historical record pertaining to 3I Atlas. And perhaps, just perhaps, they might uncover something that had eluded the attention of the professional astronomers. Part 8. The Physics of the Impossible. Let us delve into the fundamental principles governing forces. In the vast expanse of space, every entity in motion is subject to either a push or a pull from some external influence. Gravity stands as the most evident of these forces. The immense gravitational pull of the Sun dictates the orbital paths of planets and comets. Similarly, Earth's gravity is what holds our Moon in its perpetual orbit. However, gravity is not the sole force at play in the cosmos. We also have radiation pressure, which is the momentum imparted by photons of light. Then there is the solar wind, a continuous outward flow of charged particles emanating from the Sun. Furthermore, electromagnetic interactions, the complex interplay between magnetic fields and electric currents, exert their own influence. All of these forces collectively act upon comets and are capable of inducing deviations from purely gravitational trajectories. For the vast majority of comets, the most significant non-gravitational force is the propulsive rocket effect, generated by their outgassing. When ice on the sunward side of a comet's nucleus undergoes sublimation, it transforms into gaseous form and expands rapidly. This expanding gas carries with it a considerable amount of momentum. If the nucleus is also rotating, and the outgassing is more vigorous on one particular side compared to others, the resultant net momentum creates a directional thrust. This phenomenon can be likened to a leaky balloon that spins erratically as it gradually deflates. Although this effect might seem minuscule, its cumulative impact over weeks and months can become substantial. We can, in fact, estimate the magnitude of this force. Consider a comet nucleus with a radius of 1 kilometer and a density of 500 kilograms per cubic meter. This equates to a total mass of approximately 2 trillion kilograms. If this nucleus is sublimating water ice at a rate of 1,000 kilograms per second, and the resulting gas escapes at a velocity of 500 meters per second, the generated thrust would be in the order of 500,000 newtons. Dividing this force by the total mass yields an acceleration of approximately 2.5 times 10 to the power of -7 meters per second squared. This value is extraordinarily small, yet it is undeniably non-zero. Over a period of 60 days, such an acceleration would induce a velocity change of 1.3 meters per second and a positional displacement of approximately 34,000 kilometers. At the distance 3.2 Atlas is from Earth, this 34,000 kilometer displacement translates to roughly 13 arc seconds. This magnitude of deviation is indeed measurable, but it falls well within the margin of error typically associated with amateur observations. To account for the arc-minute scale, offsets that some observers are reporting, one would necessitate accelerations 10 to 20 times greater. This would imply either considerably more vigorous outgassing or the presence of an additional, unconsidered force. Could the outgassing indeed be this potent? It is a possibility, particularly if the comet is exhibiting an unusually high level of activity. Recall the pre-discovery data indicating activity at a distance of 6.5 astronomical units. This is situated far beyond the typical range where water ice is known to sublimate. For a comet to remain active at such a profound distance, it would logically need to be exceptionally rich in more volatile ices, such as carbon monoxide or carbon dioxide. These substances sublimate at significantly lower temperatures, and when they do, they produce remarkably strong outgassing. There exists another intriguing possibility. Imagine the comet's nucleus is rotating at a high speed and possesses an irregular shape. Under such circumstances, the outgassing would likely be highly asymmetric, concentrated in specific regions, and directed along particular vectors. If these directional forces happen to align in such a manner that the thrust is consistently perpendicular to the line connecting the Sun and the comet, the resulting acceleration could alter the comet's trajectory in ways that are unexpected. This precise scenario is precisely what was observed with Oumuamua. The non-gravitational acceleration detected could not be adequately explained by uniform outgassing. It necessitated some form of asymmetry, a preferred direction of thrust. Now let us consider the influence of electromagnetic effects. Comets possess ion tails composed of charged particles. These charged particles interact with the interplanetary magnetic field, which is carried by the solar wind. This interaction can generate electrical currents and impart magnetic forces. Could these forces be sufficiently powerful to exert a significant push on the nucleus itself? It is highly improbable. The mass of the ion tail is minuscule in comparison to the mass of the nucleus. Even if the ions experience substantial forces, the transfer of momentum back to the nucleus would be negligible. However, the ions themselves could be deflected, leading to the formation of tail structures that do not precisely point away from the Sun. This, in turn, could influence how we determine the center of light within the coma, potentially introducing apparent positional offsets. A more speculative possibility involves plasma interactions. The solar wind is essentially a magnetized plasma, a complex mixture of charged particles permeated by magnetic field lines. As a comet's coma and tail traverse this plasma, they inevitably disturb it, triggering the generation of waves and instabilities. Under certain specific conditions, these instabilities can give rise to localized electric fields and currents. Could such fields potentially influence the trajectory of the nucleus? While it seems unlikely, it is not entirely outside the realm of possibility. If the nucleus were to accumulate a net electric charge, and if the surrounding plasma possessed the requisite structured configuration, a minor electric force could indeed be exerted. The magnitude of such a force would be entirely dependent on numerous unknown variables, including the specific charge of the nucleus, the strength of the electric field, and the density of the plasma. What about gravitational anomalies? Is it conceivable that some unseen mass in close proximity to 3I Atlas could be perturbing its orbit? Perhaps a small asteroid, or even a fragment that has detached from the nucleus itself. The force of such a perturbation would be directly proportional to the mass of the unseen object, and inversely proportional to the square of the distance. To produce effects of any significant magnitude, one would either require a substantial mass situated very close, or a moderately sized mass positioned somewhat closer. However, if another celestial object were indeed nearby, it is highly probable that our observational surveys would have already detected it, as our sky mapping capabilities are quite advanced. Therefore, this particular explanation appears rather weak, unless the hypothetical object is unusually dark and exceedingly small. Let us take a step back and reevaluate. What are we fundamentally attempting to explain? We are trying to account for the assertions made by some amateur astronomers regarding observed anomalies in both position and brightness. However, before we resort to invoking exotic physical principles, it is prudent to first consider the more straightforward explanations. Perhaps these observed anomalies are not genuine. They might be artifacts arising from measurement errors, calibration mistakes, or simply wishful thinking. This constitutes the null hypothesis. The onus of proof rests squarely upon those who claim the existence of anomalies to rigorously demonstrate that their observations are both robust and reproducible. If indeed these anomalies are proven to be real, then we must seek a plausible physical mechanism to explain them. Asymmetric outgassing emerges as the most probable candidate. This phenomenon is well established in the study of comets. It has been observed in numerous comets, and it possesses the capacity to produce effects of the required magnitude. However, if outgassing alone proves insufficient to fully explain the observed phenomena, we would then be compelled to explore less conventional hypotheses. These might include plasma interactions, charge accumulation, or fragmentation. Each subsequent step would lead us further away from the comfortable confines of established textbook physics and into the speculative domain of educated conjecture. And if none of these hypotheses prove adequate, if we exhaust all conventional explanations and still find ourselves unable to reconcile the observations, then we would indeed be venturing into uncharted territory. It is at this point that scientists might begin to propose truly speculative theories, leading to the publication of papers with titles such as Anomalous Acceleration of Interstellar Object 3I Atlas, Implications for Composition and Activity. This is also when scientific conferences become particularly engaging. However, we have not yet reached that juncture. We remain in a phase where the majority of scientists likely believe the observations to be erroneous and the underlying physics to be entirely conventional. The 15th of December will serve as the ultimate test. If the alignment produces a measurable effect that cannot be dismissed as error or noise, then the prevailing scientific conversation will undoubtedly shift. Until that definitive moment arrives, All of this remains purely speculative. Part 9. Signals from the Silent Universe. In the year 1974, humanity embarked on a momentous undertaking by transmitting a message into the vastness of space. The Arecibo radio telescope, situated in Puerto Rico, broadcast a sequence of binary digits towards the globular cluster Messier 13, which lies a staggering 25,000 light-years away. This message encoded fundamental information about humanity, our biological makeup, our physical appearance, and our solar system. For the most part, it was a symbolic gesture. The signal is projected to reach its destination in 25 millennia. And even if it were to be received immediately and a response dispatched without delay, we would not hear back for an additional 50,000 years. Nevertheless, the act of transmission itself carried profound significance. It was a declaration. We exist, we are intelligent, and we are actively listening. Since that pivotal moment, our vigil has continued. The search for extraterrestrial intelligence, or SETI, has employed radio telescopes across the globe to meticulously scan the heavens for any indication of artificial signals. The underlying premise is elegantly straightforward. If another civilization were to attempt communication across interstellar distances, radio waves represent an exceptionally efficient medium. They travel at the speed of light, are unimpeded by interstellar dust and gas, and at specific frequencies, such as the one emitted by neutral hydrogen at 1.42 gigahertz. They act as universal beacons that any technologically advanced species would likely recognize. For decades, SETI has engaged in this painstaking listening campaign, and for decades, the only response has been an overwhelming silence. Oh, there have been fleeting candidates, brief signals that initially sparked considerable interest. The celebrated WOW signal in 1977 and BLC-1 in 2020. Each instance was met with a surge of excitement, only to be followed by disappointment when the signal failed to repeat or was eventually attributed to a terrestrial origin. The profound nature of this silence has prompted some scientists to question whether our current search methodologies are indeed the most effective. Perhaps radio waves are not the preferred mode of communication for advanced civilizations. They might employ lasers, neutrinos, or even methods that currently lie beyond our comprehension. Alternatively, it is possible that they have no intention of communicating with us at all. This line of reasoning leads us to the concept of techno-signatures. Instead of actively searching for deliberate transmissions, we endeavor to detect evidence of technology itself. This could manifest as colossal structures that obscure starlight, industrial pollutants detected in the atmospheres of exoplanets, waste heat generated from energy consumption, and, most relevant to our current discussion, interstellar probes, objects designed to traverse the vast distances between stars, equipped with instruments, power sources, and potentially communication apparatus. Could 3I Atlas conceivably be such an object? Let us meticulously examine the prerequisites for such a scenario. First and foremost, an adequate power source would be essential. Solar panels would be functional in the vicinity of a star, but entirely ineffective in the emptiness of interstellar space. Nuclear power presents a viable alternative. A single kilogram of enriched uranium, for example, can yield approximately 24 million kilowatt-hours of energy. This energy output would be more than sufficient to power a modest spacecraft for an extended duration. Another option would be radioisotope thermoelectric generators, the very technology utilized in spacecraft like Voyager and Cassini, which are capable of providing a consistent power supply for decades. Second, a sophisticated communication system would be indispensable to transmit signals across interstellar distances. This necessitates either exceptionally high power output or a substantial antenna, or ideally, a combination of both. The power requirements escalate in direct proportion to the square of the distance. At 1.6 astronomical units from Earth, The distance 3I Atlas is projected to be on December 15th. This equates to approximately 240 million kilometers. To transmit a detectable signal over such a vast expanse using a mere 1-meter antenna, one would require approximately 10 watts of transmitter power. If one employs a narrowly focused beam and a highly sensitive receiver, this power level is certainly feasible. Indeed, a standard laptop computer consumes more power than this. However, here lies the critical caveat. Why would an interstellar probe intentionally delay its transmission until it achieves alignment with Earth? If it has been traversing the cosmos for millennia, why would the specific geometric configuration matter so significantly? One potential explanation centers on efficiency. If the probe possesses a limited power supply and aims to maximize the probability of detection, it would strategically wait until it approaches its target star and achieves an optimal geometric alignment. Transmitting during such an alignment would drastically reduce the requisite power and significantly enhance the signal-to-noise ratio. This is analogous to waiting for a clear line of sight before attempting to communicate. Another plausible rationale involves a pre-programmed triggering mechanism. It is conceivable that the probe is programmed to activate upon detecting specific environmental conditions, such as the presence of a technological civilization, discernible radio emissions emanating from the target planet, or simply a favorable geometric alignment that signifies the opportune moment to announce its arrival. It is important to reiterate that all of this remains purely speculative. At present, we possess absolutely no evidence to suggest that 3I Atlas is anything other than a natural cometary body. However, the speculation is grounded in plausible engineering principles. What would a signal emanating from 3I Atlas actually sound like? Its form would be dictated by the sender's intended message. A simple beacon signal might consist of a repetitive pulse transmitted at a specific frequency, modulated in a manner that unequivocally signals its artificial origin. Consider patterns like prime numbers, fundamental mathematical constants, or a sequential arrangement that could not possibly arise through natural processes. A more complex message might encode intricate information, including images, textual data, or details about the sender. The inherent challenge lies in rendering such a message comprehensible to a recipient who does not share our language, or even our fundamental understanding of mathematics. SETI researchers have grappled with this very problem for decades. The prevailing consensus is that any civilization possessing the technological prowess to construct an interstellar probe would also possess the intelligence to ensure their transmitted signal is patently artificial. They would likely incorporate redundancy, employ error correction techniques, and utilize universal concepts that transcend cultural boundaries. If we were to receive such a signal from 3I Atlas on December 15th, the message would be unmistakable. The inherent pattern would be unequivocally clear. However, there exists a rather unsettling possibility. What if the signal is not intended for us at all? What if 3I Atlas is merely a relay station, facilitating the transmission of messages between distant nodes of a galactic network? In such a scenario, we would essentially be eavesdropping on a conversation to which we are not privy. The signal might not be designed for straightforward interpretation. It could be encrypted or compressed in ways that would render it indistinguishable from random noise to our instruments. We would detect the carrier wave, the undeniable evidence that something is being transmitted, but we would be utterly incapable of comprehending its content. This hypothetical scenario is simultaneously captivating and deeply frustrating. It would unequivocally confirm that we are not alone in the universe. It would provide irrefutable proof that interstellar communication is not only possible but is actively occurring. Yet, it would also inevitably foster a sense of being outsiders, akin to primitives observing a conversation among adults, without an invitation to participate. Does that strike you as preferable to an utter lack of sound? I confess I'm uncertain. There's another perspective worth exploring. What if the object known as 3I Atlas isn't actively transmitting signals? but rather acting as a reflector? Envision a civilization residing in a distant part of the cosmos, eager to establish contact with humanity. However, they find the prospect of a 50,000-year wait for a two-way exchange to be impractical. Their ingenious solution could involve utilizing an interstellar object as a cosmic mirror. They would dispatch a transmission towards this object, carefully timing its arrival for when the object would be perfectly positioned between their world and ours. The object would then bounce the signal back, and we would detect it. The primary benefit of this method lies in its speed. While the journey from the source to the reflector might span years, once the signal is reflected, it would reach us in mere minutes. This drastically reduces the overall communication duration compared to a direct transmission. For such a system to function effectively, the reflector would need to possess exceptionally high reflectivity at the specific frequencies being used, and it would require precise orientation. These are considerable prerequisites. However, for a civilization capable of undertaking interstellar engineering, this might well be an achievable feat. They could potentially populate their galaxy with strategically placed reflectors, allowing them to communicate with nascent civilizations as they develop their radio astronomy capabilities. The 15th of December could represent one such opportune window for communication, a precise moment when Earth, the object 3I Atlas, and a distant transmitter all align perfectly. I wish to be perfectly clear. I do not subscribe to the notion that 3I Atlas is an alien craft. I also do not anticipate it will transmit anything on December 15th. The evidence supporting such extraordinary claims is entirely absent. Nevertheless, this hypothetical scenario serves to highlight a crucial aspect of our quest for extraterrestrial intelligence. We are not solely engaged in passive listening. We are actively observing our surroundings for anything that deviates from expected patterns, for any indication of intent, design, or purpose. When an object of interstellar origin exhibits peculiar behavior, even if a perfectly natural explanation exists, our minds instinctively gravitate towards the possibility of encountering the machinations of another intelligence. This inherent impulse, whether fueled by hope or apprehension, is profoundly human. It is the driving force behind the search for extraterrestrial intelligence, propelling it forward despite decades of silence. And it is this very impulse that imbues December 15th with a sense of significance, even in the absence of concrete evidence. Part 10. The machine that learns to perceive the unusual. A groundbreaking astronomical survey, known as the Vera C. Rubin Observatory, commenced its operations in the year 2023. Once fully functional, this facility will capture images of the entire observable universe at intervals of mere nights, effectively creating a time-lapse chronicle of the cosmos. Every supernova, every asteroid, every star exhibiting variability, and every transient celestial event will be meticulously recorded. The sheer volume of data generated is immense, amounting to 15 terabytes every single night. Over the course of its 10-year mission, it is projected to produce approximately 500 petabytes of imagery. It is a quantity so vast that no human could possibly review it all. Even an assembly of thousands of astronomers working tirelessly around the clock would be unable to process it adequately. Consequently, we are in the process of training artificial intelligence systems to undertake this task on our behalf. These are sophisticated machine learning algorithms, neural networks, and artificial intelligence frameworks designed to identify patterns within astronomical images with greater speed and accuracy than any human observer. These systems are already actively employed in existing surveys, where they diligently flag supernova, detect asteroids, and classify galaxies, demonstrating continuous improvement year after year. One of the particularly noteworthy capabilities of these AI systems is anomaly detection. The underlying principle is straightforward. The algorithm is trained on numerous examples of typical celestial objects, stars, galaxies, comets, that behave in accordance with established physical laws. Subsequently, it is deployed to analyze new data, tasked with identifying anything that deviates from these learned patterns, anything that appears peculiar or anomalous. The algorithm is not required to comprehend the nature or cause of the anomaly. It merely needs to recognize that a particular entity differs from the norm. This methodology has already yielded significant discoveries, including stars exhibiting unusual variability, galaxies possessing bizarre structures, and transient phenomena that defy categorization within known frameworks. This approach is especially advantageous when examining objects like 3I Atlas, a comet exhibiting activity at considerable distances from the Sun, displaying extreme polarization and potentially deviating from its predicted orbital path. These are precisely the characteristics that an anomaly detection algorithm would be programmed to flag. Imagine an AI system that has been trained on the light curves of thousands of comets. It learns to recognize the typical fluctuations in brightness as a comet approaches and recedes from the Sun. Then, it is presented with the light curve of 3I Atlas. If this curve exhibits features that do not align with the training data, unexpected peaks, troughs, or gradients, the algorithm will generate an alert. A human astronomer then examines the flagged instance to determine whether it represents a genuinely noteworthy phenomenon or merely an artifact of the data. This process is currently underway, not exclusively for 3I Atlas, but for the broader population of objects within our solar system, and it is fundamentally transforming the way we discover and investigate celestial bodies. We are no longer constrained by the limitations of human attention spans or inherent biases. Machines are indifferent to whether an object is widely known or obscure. They do not experience fatigue while examining the 10,000th light curve. They simply process data and highlight outliers. In essence, they function as superior observers compared to ourselves. However, there is a correlative drawback. AI systems are susceptible to deception. They can misinterpret instrumental errors as genuine signals, and they might over-specialize in their training data, thereby failing to detect truly novel phenomena that bear no resemblance to anything they have previously encountered. Furthermore, they operate as black boxes. When a neural network flags something as anomalous, it cannot always articulate the precise reasoning behind its decision. It merely provides a probability score. The human astronomer is then tasked with interpreting the significance of this output. Consider the following scenario. In the latter part of November in the year 2025, a machine learning system analyzing observations of 3I Atlas detects an anomaly. This could manifest as a sudden fluctuation in brightness that deviates from the standard model for cometary activity. Alternatively, it might involve a shift in the orientation of the comet's tail, suggesting a change in the direction of its gas and dust expulsion. It could even be a subtle displacement in its position that becomes apparent over several nights of observation. The algorithm flags this deviation, and the alert is subsequently reviewed by a human expert, who must then make a critical determination. Is this anomaly a genuine phenomenon, or is it merely noise in the data? If it is deemed to be real, what are the subsequent steps? Ideally, this would trigger follow-up observations, involving the redirection of more telescopes towards the object, the acquisition of higher resolution imagery, spectroscopic analysis to characterize the anomaly, and an effort to understand its underlying cause. However, telescope time is a finite and valuable resource. Astronomers cannot simply abandon all other work to observe a single object unless there is a strong conviction of its importance. This necessitates a difficult judgment call. How certain are we that the anomaly is authentic? How significant would it be if it is indeed real? And how much of our limited observation time are we willing to risk on a mere possibility? This is precisely where December 15th becomes relevant. If the anomaly detection system flags something unusual concerning 3I Atlas in the weeks preceding its alignment with Earth, that alert gains amplified significance. It is no longer just an isolated anomaly. it becomes a potential precursor to a larger event, a trigger, a culmination. This narrative lends it greater compellingness, making it more deserving of intensive follow-up, even in the face of scientific uncertainty. Now, let us broaden this perspective beyond 3I Atlas. We are entering an epoch where AI systems will be continuously scrutinizing the heavens, flagging anomalies, and generating alerts. Some of these alerts will prove to be false positives. Others will indicate real but unremarkable findings. And a small fraction will represent genuinely novel phenomena that fundamentally alter our understanding of the universe. The principal challenge lies in discerning among these alerts, deciding which ones warrant serious attention and which can be disregarded. In a manner of speaking, these machines are augmenting our sensory capabilities, enabling us to perceive patterns and changes that would otherwise remain imperceptible to unassisted human observation. However, they also introduce new forms of uncertainty. When a human astronomer makes a discovery, they can articulate their observations and the rationale behind their perceived significance. When an AI flags something, the output is often reduced to a numerical score or a confidence level. One must place trust in the algorithm's underlying logic, even if its reasoning cannot be fully scrutinized. December 15th serves as a crucial test case for this emerging paradigm. If multiple AI systems, trained on diverse datasets and employing distinct architectures, all flag 3I Atlas as anomalous in the days leading up to its alignment, this would constitute a robust indicator. It would suggest that a genuine phenomenon is occurring, one that transcends the limitations of individual measurement errors or algorithmic quirks. Conversely, if these alerts are inconsistent, or if they dissipate upon careful re-examination of the data, it would imply that the anomalies were likely artifacts. Regardless of the outcome, we will gain valuable insights into the effective utilization of these tools, the art of balancing machine-generated insights with human skepticism, and the navigation of a universe where discovery is increasingly facilitated by algorithms whose inner workings remain somewhat opaque to us. Part 11. The complexities of planetary defense. In the year 2013, an asteroid measuring approximately 20 meters in diameter entered Earth's atmosphere above Chelyabinsk, Russia, detonating with an explosive force comparable to 500 kilotons of TNT. The resulting shockwave shattered windows across 6 cities, and more than 1,500 individuals sustained injuries, primarily from flying glass. This asteroid had gone completely undetected prior to its impact. We had no prior warning, insufficient time for evacuation, and no means to intercept or neutralize it. The Chelyabinsk event served as a stark awakening, demonstrating Earth's inherent vulnerability and highlighting the deficiencies in our detection systems. In response, space agencies worldwide significantly enhanced their programs for monitoring near-Earth objects. NASA established the Planetary Defense Coordination Office. The United Nations subsequently endorsed the formation of the International Asteroid Warning Network, IWARN, and the Space Mission Planning Advisory Group, SMPAG. These international bodies are responsible for coordinating observational efforts, assessing potential risks, and formulating plans for possible mitigation missions. Their primary objective is to ensure that an event like Chelyabinsk does not recur, or if it does, that humanity is forewarned. However, a fundamental tension lies at the core of planetary defense. How does one effectively communicate risk to the public without inadvertently inciting widespread panic? If an asteroid is detected with a mere 1% probability of impacting Earth within the next decade, should this information be disseminated immediately? Or is it preferable to await more precise probability assessments? Should the information be withheld entirely, with the situation managed discreetly? There is no universally agreed upon approach. Different agencies adhere to varying policies, and these policies are subject to continuous debate and revision. This is where the object 3I Atlas enters the discussion. While not technically classified as a near-Earth object, Its closest approach to our planet is a considerable 1.8 astronomical units, far exceeding the threshold for a potentially hazardous asteroid. It is an interstellar visitor, and our experience with such objects is exceptionally limited. The appearance of Oumuamua, another interstellar interloper, raised significant questions regarding the classification and communication of information pertaining to such entities. Should they be categorized alongside asteroids, comets, or as an entirely distinct class of celestial body? Some observers have put forth the speculation that 3I Atlas was briefly included on internal watch lists maintained by planetary defense organizations, not due to any perceived impact threat, but because its unusual observed behavior warranted closer scrutiny. These watch lists are typically kept confidential and are utilized for training exercises, protocol development, and interagency coordination. Objects are added to and removed from these lists based on evolving assessments of their characteristics and potential risks. The public generally remains unaware of these lists unless a situation escalates to the point of a formal warning being issued. If 3I Atlas were indeed on such a list, what would be the implications? Likely, nothing particularly alarming. It would simply signify that some entity, somewhere, deemed the object's trajectory or characteristics sufficiently uncertain to warrant additional attention. Perhaps the intention was to refine observation protocols, or to test the speed at which orbital data could be gathered and refined. It might simply represent a prudent measure of caution. However, within the realm of conspiracy theories, inclusion on a watch list is readily interpreted as evidence of concealed danger, a tacit admission by authorities that they possess knowledge they are withholding from the public. Furthermore, there is the pertinent question of disclosure protocols for potential techno-signatures. The post-detection protocols developed by the SETI community outline a series of steps to be undertaken in the event that a signal of potential extraterrestrial origin is detected. Key tenets of these protocols include rigorous verification prior to any public announcement and consultation with relevant scientific bodies. However, these are merely guidelines, not legally binding regulations. There is no enforcement mechanism in place, and they were primarily formulated with radio signals in mind, rather than the ambiguous behavior of physical celestial objects. If 3I Atlas were to exhibit characteristics suggestive of an artificial origin, who would be responsible for determining whether and when to make such information public? Would it be NASA, the European Space Agency, ESA, the International Astronomical Union, IAU, or the United Nations? The answer remains unclear, and this very ambiguity creates fertile ground for speculation. If no announcement is made, is it because there is genuinely nothing to report? Or is the announcement being deliberately delayed while experts engage in protracted debates about its implications? The broader context is crucial here. We are currently living through an era marked by a heightened degree of public skepticism towards institutions. Government agencies, scientific organizations, and media outlets are all subjected to scrutiny from significant segments of the populace. When these institutions assure the public that there is no cause for alarm, many individuals interpret this as confirmation that something is being deliberately concealed. This dynamic is observable in responses to pandemics, in the discourse surrounding climate science, and in the forecasting of space weather. And it is equally applicable to the situation surrounding 3I Atlas. From a policy standpoint, the fundamental challenge lies in striking a delicate balance between transparency and responsible communication. Excessive transparency disseminated too early can lead to widespread misunderstanding and unnecessary fear. Conversely, insufficient transparency, particularly when delivered too late, can erode public trust and fuel the proliferation of conspiracy theories. The ideal scenario involves providing accurate, timely information conveyed in a manner that the general public can readily comprehend. However, achieving this ideal is exceedingly difficult when the underlying scientific understanding itself is uncertain and continually evolving. December 15th, occupies a pivotal position at the nexus of all these complex dynamics. It represents a specific date, a moment in time when a particular event may or may not transpire, if various agencies have been meticulously monitoring anomalies in the behavior of 3I Atlas. December 15th would naturally emerge as a critical juncture, a designated point for assessing whether prior predictions hold true or if something unanticipated occurs. Should any event, however minor or explainable, manifest, the pressure to disclose information to the public will be immense. Social media platforms will undoubtedly erupt with discussions. Amateur astronomers will share their observational data, and the narrative will propagate regardless of whether official channels wish it to. Conversely, if nothing of consequence occurs, the ensuing silence will be subject to diverse interpretations. Skeptics will likely proclaim their vindication, dismissing the speculation as unfounded. Proponents of extraordinary explanations will suggest that the event was deliberately suppressed or that its true ramifications are being covertly managed. The agencies involved will most probably remain silent, preferring to allow the non-event to recede from public attention without official comment. What I find particularly compelling is how this situation illuminates the limitations of our existing governance frameworks in addressing cosmic phenomena. We possess established protocols for managing known threats, such as asteroids. We also have protocols in place for handling potential extraterrestrial signals. However, we lack specific protocols for navigating ambiguous situations where an object exhibits peculiar behavior without posing an immediate threat. These are scenarios characterized by scientific uncertainty coupled with significant public interest, where the distinction between a natural phenomenon and an artificial object becomes blurred. December 15th may well compel us to develop such protocols, or it might simply fade into obscurity as another footnote in the extensive history of cosmic false alarms. Regardless of the eventual outcome, it will undoubtedly serve as a valuable learning experience. Part 12. When the sun exhibits erratic behavior, the sun is not a star characterized by stability or predictable conduct. It is in fact a tumultuous sphere of plasma, permeated by magnetic fields that twist and snap with the intensity of overstretched rubber bands. Periodically, these magnetic fields discharge their stored energy through explosive phenomena known as solar flares and coronal mass ejections. These eruptive events propel billions of tons of charged particles into space at velocities ranging from several hundred to over 1,000 kilometers per second. Upon reaching Earth, these particles interact with our planet's magnetic field, triggering geomagnetic storms. For the most part, these storms are relatively minor. They produce spectacular auroral displays and may cause some interference with radio communications. However, on occasion, they can become severe. In 1859, the Carrington event, the most significant geomagnetic storm in recorded history, generated auroras visible as far south as the Caribbean and ignited telegraph systems. A storm of comparable magnitude occurring today could inflict damage on satellites, disrupt global positioning systems, and cause widespread power grid failures across entire continents. The primary challenge lies in accurate prediction. We possess the capability to detect coronal mass ejections as they depart from the Sun and can estimate their arrival time at Earth, which typically falls within a few hours. However, forecasting their precise impact is a far more complex undertaking. The intensity of a geomagnetic storm is contingent upon the orientation of the magnetic field embedded within the ejected plasma. If this field is aligned in opposition to Earth's magnetic field, efficient coupling occurs, resulting in a powerful storm. Conversely, if the fields are aligned in parallel, the coupling is weak, and the storm is considerably milder. We are unable to measure this magnetic field orientation until the plasma reaches satellites strategically positioned in the space between the Sun and Earth, approximately 1 hour before its projected impact. This provides a very limited window for warning. In the year 2025, the Sun is nearing the zenith of solar cycle 25. Consequently, activity levels are elevated, with frequent solar flares and coronal mass ejections. Space weather forecasters are actively engaged in issuing alerts and monitoring for significant events. This is where the situation becomes particularly intriguing. What if, around December 15th, we were to experience an unexpected geomagnetic storm? What if a coronal mass ejection were to arrive at Earth precisely at the moment when 3I Atlas is in alignment? How would we differentiate a disturbance originating from the Sun from a hypothetical effect attributed to the comet? The answer is that we likely would not be able to, at least not immediately. Both scenarios would produce analogous signatures: heightened auroral activity, fluctuations in Earth's magnetic field, increased radiation levels detected by satellites, and disruptions to radio communications. The timing would undoubtedly raise suspicion, but temporal coincidence alone does not establish causation. Correlation does not equate to causality. Even if a geomagnetic storm were to coincide exactly with the December 15th alignment, it could simply be a matter of chance. However, let us delve deeper. Solar storms possess a discernible structure, characterized by their rise times, peak intensities, and decay patterns that conform to established physical principles. The specific characteristics of a storm are dependent on the velocity and magnetic configuration of the coronal mass ejection responsible for it. Space weather scientists can frequently trace the origin of a storm back to its solar source, identifying the particular flare or eruption that generated it. If a storm were to arrive on December 15th and we could unequivocally pinpoint its solar origin, the question would be definitively resolved. It is solar, not cometary. However, what if the storm's characteristics do not precisely align with the identified solar event? What if its intensity is greater than anticipated? Or if the magnetic field orientation is unusual? Or if secondary peaks are present that deviate from the standard profile? In such instances, we enter a realm of ambiguity. It is possible that our models of the solar wind are incomplete, or that the plasma experienced additional acceleration en route to Earth. Or perhaps, just perhaps, there is a contribution from an alternative source. I would like to guide you through a hypothetical scenario, one that is speculative but grounded in physical principles. Imagine that the ion tail of 3I Atlas contains magnetic structures, specifically flux ropes, which are formed through the interaction of the comet's outflowing plasma with the interplanetary magnetic field. These structures would be propagating outward from the comet at the speed of the solar wind, approximately 400 kilometers per second. On December 15th, Earth would be positioned downstream of the comet at a distance of roughly 1.6 astronomical units, equivalent to 240 million kilometers. At a velocity of 400 kilometers per second, material released from the comet would require approximately 7 days to reach Earth. Now, let us suppose that around December 8th, a week prior to the alignment, the comet undergoes a sudden surge in activity, perhaps an outgassing burst, or a fragmentation event, leading to the release of a substantial quantity of ionized material into its tail. This material would then be swept along by the solar wind, heading towards Earth. By December 15th, when the precise geometric alignment is achieved, this augmented plasma stream reaches Earth's magnetosphere. Concurrently, the Sun happens to eject a coronal mass ejection. While not directly aimed at Earth, it passes sufficiently close to graze our magnetosphere. The combined effect of these two phenomena, the solar and the cometary, arriving simultaneously, results in a geomagnetic disturbance that is more intense or complex than what the solar contribution alone would produce. Could we detect the cometary contribution? It is possible. If spacecraft were positioned to monitor the solar wind upstream of Earth, they might detect anomalies in the composition of the plasma. The comet's expelled material might exhibit distinct proportions of elements and their isotopes When contrasted with plasma originating from the Sun, it is conceivable that it could contain elevated levels of carbon or nitrogen. Furthermore, it might display spectral characteristics indicative of cometary molecules. Should instruments be calibrated to detect these specific signatures, they could potentially be identified. However, here lies the predicament. We are not actively searching for them. The probes currently traversing the solar wind are engineered to monitor solar emanations, not contributions from comets. They ascertain broad plasma attributes such as density, speed, and magnetic field intensity. They do not routinely perform in-depth compositional analyses. Consequently, any cometary signature, if present, could pass unnoticed. The ensuing disturbance would be solely attributed to the solar event, and the 15th of December would conclude without anyone realizing that 3I Atlas had made a modest yet quantifiable contribution to Earth's space environment. This is the disheartening aspect of ambiguous occurrences. Even when they transpire and produce tangible effects, they can be obscured by other phenomena, or overlooked due to our inability to detect them. Science does not operate as a flawless observer. We perceive that which our instruments are designed to measure and interpret our observations through the framework of our established models and preconceptions. If an effect falls outside this established paradigm, it can remain invisible. There is one further perspective to contemplate: false positives. The prediction of space weather is an imprecise discipline. At times, forecasters anticipate a significant storm, and nothing materializes. The coronal mass ejection misses Earth, or its magnetic field orientation proves unfavorable, or it dissipates during its journey. Conversely, at other junctures, a storm arrives with minimal forewarning because the solar eruption occurred on the far side of the Sun, and only became discernible as it entered Earth's line of sight. If forecasters predict heightened geomagnetic activity for December 15th, and it fails to manifest, what conclusion can be drawn? It could signify that the prediction was erroneous. Alternatively, it might indicate something else entirely. Perhaps the anticipated solar storm was genuine, but it was counteracted or diverted by plasma, originating from 3I Atlas. It is conceivable that the planetary alignment created a shielding effect, thereby diminishing the storm's impact. Once more, this is highly speculative, but it serves to illustrate the profound difficulty in interpreting null results. The absence of an anticipated effect can be as enigmatic as the presence of an unexpected one. My central point is this: December 15th exists within a space weather milieu that is inherently complex and unpredictable. The Sun exhibits considerable activity, coronal mass ejections are frequent occurrences, and Earth's magnetosphere is perpetually subjected to the variable solar wind. Against this backdrop of pervasive noise, discerning a subtle contribution from an interstellar comet would present an immense challenge. It is akin to attempting to detect a whisper amidst the din of a crowded room. Even if the whisper is present and conveying something of importance, it may still be missed. This does not imply that we should cease our efforts. The networks dedicated to monitoring space weather are now more sophisticated than ever before. We possess an array of satellites, ground-based magnetometers, radar systems, and auroral cameras, all feeding data into real-time analysis platforms. Should any unusual event unfold on December 15th, it will undoubtedly be recorded. The pertinent question is whether anyone will recognize its significance at the time, or if it will only be unearthed retrospectively when researchers meticulously sift through archival data in pursuit of anomalies. And this leads me to a sobering reflection. How many peculiar events have already transpired that have eluded our detection? How often has the universe offered a subtle intimation, only for us to remain oblivious? We are only capable of discovering what we actively seek, and we tend to search in areas where we anticipate finding something. Everything else tends to slip through the observational sieve. December 15th might represent one such oversight. or it could potentially mark the moment when our attention is finally drawn. Part 13. Fast radio bursts and the enigma of cosmic static. In 2007, astronomers were meticulously examining archived data from the Parkes Radio Telescope in Australia when they encountered something entirely unexpected. It was a radio wave pulse, lasting a mere few milliseconds, yet possessing an energy equivalent to the sun's entire daily emission. The pulse exhibited a distinctive dispersion pattern, wherein different frequencies arrived at slightly staggered intervals, signifying its passage through vast expanses of ionized gas. The inference was unavoidable. This pulse had originated from far beyond the confines of our own galaxy, at a distance spanning billions of light years. They christened it a fast radio burst, or FRB. Initially, it was perceived as an isolated incident, a solitary detection that could potentially be attributed to instrumental error or terrestrial interference. However, subsequent investigations revealed more such signals. Dozens, then hundreds were identified. Some repeated, while the majority did not. Their origins remained shrouded in mystery. Magnetars, ultra-dense neutron stars characterized by their formidable magnetic fields, emerged as a prominent candidate. The collision of black holes presented another plausible explanation, and, inevitably, some posited that these could be of artificial origin, signals emanating from extraterrestrial civilizations, or pulses transmitted via interstellar communication networks, thereby suggesting that humanity is not alone. The hypothesis of an artificial source is regarded as a fringe theory by the majority of astronomers, as natural explanations appear sufficient to account for the observed characteristics. However, the reality is that we do not definitively know what causes them. Every proposed natural model encounters difficulties, and each attempt to explain the diverse, observed properties necessitates either extraordinary circumstances or precise fine-tuning. The enigma persists, and such mysteries invariably fuel speculation. Fast-forwarding to 2025, FRB detections have become commonplace. Observatories worldwide are equipped with instruments specifically designed for their detection and characterization. The catalog now enumerates thousands of such events. And among these events, some are genuinely peculiar. Repeating bursts exhibit periodicity, implying their origin from a rotating celestial body. Bursts display complex subpulse structures, hinting at multiple emission zones. Some bursts cluster in time, appearing in groups separated by extended periods of silence. Now, envision this scenario. On December 15th, 2025, concurrent with 3I Atlas achieving its alignment with Earth, radio telescopes register a fast radio burst. The timing appears coincidental, does it not? FRBs occur with considerable frequency. On any given day, multiple FRBs are detected somewhere across the globe. Therefore, the detection of one on December 15th would not, in itself, be particularly noteworthy. This would be the case unless the FRB exhibited unusual properties, unless its dispersion measure, the parameter indicating its travel distance, suggested an origin inconsistent with a distant extragalactic source, or unless its directional arrival, when triangulated by multiple observatories, pointed disconcertingly close to the celestial position of 3I Atlas. Such a confluence of factors would be considerably more challenging to dismiss as mere coincidence. The probability of a random FRB originating from the vicinity of 3I Atlas at the precise moment of alignment would be exceedingly small, not zero, but sufficiently minute to provoke considerable interest. And if the FRB possessed other anomalous characteristics, such as repeating with a pattern suggestive of intelligence, the level of intrigue would escalate dramatically. Let me clarify the probabilities involved. The celestial sphere encompasses approximately 41,000 square degrees. If FRBs were distributed uniformly across the sky at a rate of a few per day, the likelihood of detecting one within any specific square degree region on any given day would be approximately 1 in 10,000. 3i Atlas occupies a minuscule fraction of a single square degree. Consequently, the a priori probability of such a coincidence is genuinely infinitesimal. Its occurrence would necessitate an explanation. However, this is where the situation becomes more intricate. The detection of FRBs is not uniformly distributed across the sky. Observatories often have preferred pointing directions dictated by their observation schedules. Furthermore, on December 15th, if both amateur and professional astronomers are diligently observing 3i Atlas due to the heightened anticipation surrounding its alignment, radio telescopes might also be directed towards that particular region of the sky. This would not necessarily be for the purpose of searching for FRBs, but rather to investigate potential radio emissions originating directly from the comet itself. And when one is actively observing a specific patch of the sky, the probability of detecting an event from that region increases simply because it is under observation. This inherent selection bias complicates the interpretation. Was the FRB genuinely associated with 3i Atlas, or did we merely capture a random FRB by chance because our instruments were focused in that direction? Disentangling these possibilities demands rigorous statistical analysis and, ideally, data from multiple observatories that were not specifically focused on the comet. There exists another scenario worthy of consideration. Imagine, for a moment, that 3i Atlas itself emits a radio pulse. This would not be classified as a fast radio burst in the technical sense, given that FRBs are extragalactic in origin. Instead, it would be a transient radio signal, a burst of electromagnetic radiation triggered by some event occurring within the comet's coma or tail. Plasma instabilities are known to generate radio waves. Lightning discharges within dusty cometary environments have been proposed as a potential mechanism, though they have yet to be definitively observed. If such a discharge were to occur within 3i Atlas during the period of alignment, it might produce a detectable radio signal. This signal would be considerably weaker than an FRB, as it would emanate from a relatively nearby object, rather than from billions of light years away. However, at a distance of 1.6 astronomical units, a moderately powerful emission could still be discernible by sensitive radio telescopes. Such a signal would possess distinct characteristics compared to an FRB. It would exhibit little to no dispersion, as the radio waves would not have traversed intergalactic space. Its frequency range might be broader, less narrowly defined, and its duration potentially longer. If radio astronomers were to detect such a signal on December 15th, it would represent a genuine scientific discovery, providing evidence of a novel form of cometary activity, a mechanism for electromagnetic emission not currently incorporated into existing models. The resultant scientific publications would be profoundly intriguing, but this would not constitute evidence of intelligence or an artificial origin. It would simply represent a facet of physics that we were previously unaware comets could exhibit. The primary challenge lies in the fact that detecting radio emissions from comets necessitates precise knowledge of where and when to direct observations. The vast majority of radio telescopes are habitually aimed at distant galaxies, quasars, and pulsars. Directing them towards a comet is an atypical undertaking, typically requiring a specific request, and telescope observation time is a precious commodity. Therefore, unless there exists a compelling justification for observing 3i Atlas at radio wavelengths on December 15th, such an observation is unlikely to occur. However, this is precisely where the burgeoning online speculation could prove beneficial. If a sufficient number of astronomers are actively discussing December 15th, and if the alignment date becomes widely recognized within the scientific community, it is conceivable that someone might elect to point a radio telescope towards the comet, simply to explore the possibilities. This is the kind of initiative a graduate student might undertake, utilizing a few hours of observation time on a less powerful instrument to investigate potential radio emissions, either to rule them out or to potentially uncover something novel. It represents a low-risk endeavor with potentially high rewards. Thus, an intriguing feedback loop emerges. Speculation spurs observation, which in turn generates data, thereby either corroborating or refuting the initial speculation. In the most favorable outcome, we acquire new knowledge about comets. In the less favorable scenario, we accumulate additional data that enhances our understanding, even if it yields null results. In either case, the speculation holds intrinsic value if it motivates concrete scientific inquiry. And perhaps this is the true significance of December 15th. Not that something dramatic is likely to occur, but rather that individuals are paying attention, that an otherwise routine astronomical event has captured sufficient imagination to stimulate serious scientific scrutiny. The universe teems with wonders that often go unnoticed simply because no one is actively observing them. On this occasion, at the very least, people are looking. Part 14. The question that transforms everything. Allow me to guide you back to the fundamental principles, to the core question that underpins all this speculation, all this analysis, and all this anticipation. The paramount question is not what 3i Atlas will do to Earth. Instead, the question is, are we alone? Every quest for anomalies, every hypothesis concerning artificial origins, every hope that December 15th might usher in something unforeseen, ultimately traces back to that deeper, more profound inquiry. We have been posing this question for as long as we have gazed upwards at the celestial expanse. Ancient philosophers pondered the existence of other worlds beyond our own. Medieval scholars debated whether the divine being would create life elsewhere in the cosmos. In the 20th century, scientists constructed radio telescopes with the explicit aim of detecting extraterrestrial signals. And now, in 2025, we are observing an interstellar visitor, contemplating the possibility that it might be carrying a message. Statistical probabilities suggest that we should not be alone. Our galaxy harbors an estimated 100 to 400 billion stars. Recent surveys of exoplanets indicate that the majority of stars are orbited by planets. Potentially habitable worlds, planets situated within the temperature range conducive to supporting liquid water, number in the billions, confined solely to the Milky Way. The universe has had 13.8 billion years to foster the development of life, intelligence, and technology. The fundamental building blocks are abundant, and the temporal duration has been sufficient. So, where is everyone? This is the Fermi paradox, named after the physicist Enrico Fermi, who famously posed it during a casual lunch discussion in 1950. If intelligent life is indeed widespread, we ought to have encountered evidence of it. Megastructures, radio signals, probes visiting our solar system. The conspicuous absence of such evidence, the profound silence, represents one of the most significant enigmas in scientific inquiry. Perhaps life itself is exceedingly rare. Perhaps intelligence is even rarer. It is possible that civilizations invariably self-destruct before achieving the capacity for interstellar travel. Alternatively, they might exist but choose to remain concealed. It is also conceivable that they are present among us, yet we fail to recognize them. 3i Atlas serves as a test case for one manifestation of this latter hypothesis. If advanced civilizations utilize interstellar objects as vessels for probes or communication devices, then every object that traverses our solar system from interstellar space holds potential significance. We cannot dismiss any of them without thorough examination. Oumuamua, for instance, demonstrated its peculiar acceleration, its unusual form, and its failure to outgas, all features that remain inadequately explained. Mainstream scientific consensus has converged on naturalistic explanations involving hydrogen ice or unconventional cometary compositions. However, a minority of researchers, including distinguished astronomers, maintain that an artificial origin continues to be a viable hypothesis. With 3i Atlas, we are presented with a second opportunity. a second chance to apply all that we have learned from Oumuamua. We possess superior instruments, a greater number of observers, and earlier detection capabilities. If there is any artificial aspect to this object, we stand a better prospect of identifying it than we did with Oumuamua. Furthermore, December 15th, with its specific alignment geometry, represents a natural experiment, a critical juncture at which any deliberately timed signal or effect would likely manifest. However, I wish to momentarily shift our perspective. Suppose our assumptions are incorrect. Suppose there is nothing artificial about 3I Atlas. Imagine that December 15th arrives and passes without the detection of any anomalies, signals, or unexpected phenomena. What does this signify? Does it imply that we are alone? Assuredly not. It merely indicates that one interstellar comet, out of the 3 detected objects of this kind, was not artificial. This hardly constitutes a comprehensive survey. The endeavor to search for extraterrestrial intelligence is a protracted undertaking. It may span centuries, or it might extend over millennia. Alternatively, it could occur imminently, when a radio telescope intercepts an unmistakable signal, when a probe reveals its presence, or when an event transpires that leaves no room for doubt. We are uncertain about the temporal scale involved, and we do not know the precise odds. We only know that if we cease our search, we effectively guarantee that we will never discover anything. December 15th holds significance not because it is statistically probable to yield a dramatic revelation, but because it represents a distinct, testable moment. We have the capacity to direct our instruments, to gather data, and to subsequently analyze and interpret it. If something occurs, we document it. If nothing occurs, we meticulously record that as well. Either outcome contributes to the expansion of our knowledge. Either result serves to narrow the spectrum of possibilities. There is a profound aspect to standing upon a planet, hurtling through the vastness of space, observing an object originating from a distant star system as it glides past, and contemplating the possibility that it might be carrying a message from beings we have never encountered. This act embodies optimism, hope, and a reaching beyond the confines of our lived experiences towards something immeasurably greater. Even if the answer proves to be negative, even if we find ourselves speaking to an empty room, the very act of asking the question instigates a transformation within us. It serves as a poignant reminder that we are an integral part of something far larger than our individual existences or even our collective civilization. The esteemed astronomer Carl Sagan once eloquently stated that the cosmos resides within us, that we are composed of stellar matter, engaged in the contemplation of the stars. He was undeniably correct. However, the connection runs deeper than mere chemical composition. We represent a means by which the universe comprehends itself. And if other sentient beings exist out there, other minds grappling with the same fundamental questions, gazing upon the same celestial panorama, then we are inextricably linked to them through the shared curiosity, through the simple, innate act of wondering. 3I Atlas is, in all likelihood, almost certainly, composed of mere rock and ice. But even if it is simply a comet, it is a comet that originated from a distant locale. It carries within it information pertaining to a different sector of the galaxy, insights into the composition of interstellar clouds, the processes governing the formation of planetary systems, and the mechanisms that shape matter across immense distances and vast epochs. That information is inherently valuable. Its narrative is profoundly worth understanding, and if, against all odds and in defiance of all reasonable expectations, it proves to be more than just rock and ice, if December 15th unveils something we had not anticipated, then everything will irrevocably change. Not solely our scientific understanding or our technological capabilities, but our very perception of our place within the cosmos, our fundamental understanding of who we are and what we might ultimately become. This is what is truly at stake, It is not our physical safety that is imperiled. Earth will remain unharmed, irrespective of the actions or inactions of 3i Atlas. What is at stake, however, is our cosmic solitude, our philosophical isolation, the fundamental question of whether we represent the universe's sole attempt at self-awareness, or if we are but one entity among a multitude. December 15th will not provide a definitive answer to this question, but it may offer a subtle clue, a faint hint, a direction for further investigation. And at times, that is precisely what is needed. Part 15, The Vigil. And so, we find ourselves at this juncture. We are in the days preceding December 15th, 2025. Across the globe, telescopes are precisely aimed at a specific region of the sky where 3i Atlas traverses its hyperbolic trajectory. Amateur astronomers are diligently preparing their equipment, meticulously calibrating their cameras, and finalizing their observation schedules. Professional observatories are engaged in their routine surveys, which will inevitably capture the comet alongside thousands of other celestial objects. Space weather forecasters are intently monitoring the sun for any signs of coronal mass ejections. Radio astronomers are attentively listening to the cosmic symphony for fast radio bursts and any unusual signals. The majority of these individuals anticipate nothing out of the ordinary. They are engaged in the practice of science, amassing data, and adhering to established protocols. December 15th is merely another date on the calendar, another night dedicated to astronomical observation. However, a subset of these individuals harbors a sense of contemplation. Some are observing with an elevated degree of attentiveness, infused with a modicum of hope, trepidation, or sheer curiosity. They are wondering if this particular night might be the one upon which something fundamentally changes. Allow me to elucidate what you should be looking for if you wish to follow along. Firstly, space weather. The National Oceanic and Atmospheric Administration, or NOAA, operates a space weather prediction center that furnishes real-time data concerning solar activity and geomagnetic conditions. Their website prominently displays current auroral forecasts, parameters of the solar wind, and geomagnetic indices. Should Earth's magnetosphere experience any unusual disturbances on December 15th, these anomalies will be reflected in those data streams within a matter of hours. Look for significant spikes in the K-index, a metric used to quantify geomagnetic activity. Observe for reports of auroras appearing at latitudes where they are not typically visible. Note any communications from satellite operators reporting anomalies or disruptions in their communication systems. Secondly, positional data. The Jet Propulsion Laboratory's Horizon system provides ephemeris predictions for 3i Atlas that are readily accessible online. If you possess access to observational data, whether your own or that shared by others, you can compare the measured positions with the predicted positions. Any persistent offset exceeding a few arc minutes, corroborated by multiple independent observers, would be considered highly significant. Online forums such as the Minor Planet mailing list and various amateur astronomy communities on Reddit serve as platforms where such observations are frequently shared and discussed. Thirdly, photometry. Light curves, which graphically represent 3i Atlas's brightness over time, are currently being compiled by amateur observers. If the comet exhibits any unexpected increases or decreases in brightness, or significant fluctuations on December 15th, these phenomena will become apparent in the photometric data. The crucial challenge lies in discerning genuine variations from the inherent measurement noise and the effects of atmospheric conditions. Corroborated findings from multiple independent observations lend significantly more credibility than isolated reports. Fourth, radio wave investigations. This presents a greater hurdle for casual observers, as real-time data from radio telescopes is seldom made public. However, SETI organizations and certain university radio observatories do occasionally release updates on their observations. Should a notable radio transient be identified emanating from the vicinity of 3 Atlas, an announcement would likely surface within days via astronomers' telegrams or similar communication channels. Fifth, social media and news dissemination. If any genuinely extraordinary event occurs, word of it will disseminate rapidly. Scientists will share updates on Twitter. Discussions on online forums will erupt. News organizations will pick up the story. The challenge lies in discerning valid information from misinformation within this torrent of data. Numerous claims will be amplified beyond their significance or misunderstood. Some will be entirely fabricated. Critical assessment and verification of sources are paramount. Now, what are the plausible outcomes? The most probable scenario is that December 15th passes without incident. 3 Atlas will continue on its projected path, its luminescence dimming as anticipated. No radio signals will be detected. Solar weather conditions will remain within expected parameters. Amateur observers will notice nothing out of the ordinary, and interest will gradually wane in the ensuing weeks. The speculation will fade into obscurity. 3 Atlas will become a minor mention in the history of celestial events. Another interstellar traveler that arrived and departed without fanfare. This represents a null result. While potentially disappointing to those anticipating something extraordinary, it remains scientifically valuable. Null results confirm the efficacy of our current models. They indicate our understanding of comets is sufficient to forecast their behavior, and that interstellar objects, at least those we have detected, are natural occurrences that do not necessitate unusual explanations. The second possibility involves minor deviations, small divergences from projected trajectories, a brief geomagnetic fluctuation that may or may not be linked to the alignment, a fleeting episode of increased brightness lasting a few hours, positional measurements by amateur astronomers showing discrepancies only marginally above the background noise. These types of equivocal signals would spark discussion, but not a paradigm shift. Scientists would engage in debates regarding their interpretations. Some would assert the anomalies are genuine and significant. Others would attribute them to instrumental errors or chance occurrences. Scholarly articles would be published. Conference sessions would be dedicated to the topic, yet no definitive conclusion would be reached. The third scenario, a groundbreaking revelation, is the least probable but carries the most profound implications. A clear, undeniable signal, a repeating radio pulse exhibiting mathematical regularity, a fluctuation in brightness that conveys encoded information, a positional shift so substantial that it could only be explained by active propulsion, satellite malfunctions that align precisely with the timing of the celestial alignment and cannot be attributed to solar activity. In this eventuality, we would possess tangible evidence that 3 Atlas is not entirely a natural phenomenon. The scientific community's response would be immediate, involving follow-up observations utilizing every available instrument, emergency consultations among international space agencies, the activation of post-detection protocols, and ultimately public dissemination of the findings. Such a discovery could not be kept clandestine. Which scenario will unfold? I cannot say. No one can. This is precisely why December 15th holds significance. It represents a genuine unknown, a roll of cosmic dice. Regardless of whether the outcome is mundane or extraordinary, we will gain knowledge. However, here's what I wish for you to retain. The importance of December 15th is not truly about the events of that specific date. It is about what it symbolizes, a moment when humanity across the globe collectively directs its gaze outward, observing an object originating from another star system, posing questions about its nature and origin. This shared attention, this collective curiosity, is infrequent and precious. On most days, most individuals are preoccupied with internal matters, immediate concerns, local issues. and personal lives, which is entirely understandable and necessary. Yet, periodically, we need to look up to remind ourselves that we are part of something immense, mysterious, and wondrous. 3 Atlas has provided us with a reason to look skyward. Whether it is merely a comet or something more, it has connected us to the broader cosmos in a tangible manner. It has served as a reminder that space is not a void, that objects traverse interstellar distances, and that our solar system is situated within a dynamic galactic neighborhood. Furthermore, it has prompted us to contemplate whether we are alone, whether other intelligences are observing their own skies and pondering similar questions. These inquiries will not be answered on December 15th. They will be addressed over decades and centuries through diligent observation, rigorous analysis, and occasional fortunate discoveries. December 15th is but a single data point in this extended quest. However, it is our data point, our juncture, our opportunity to observe and contemplate. Therefore, observe if you are able. Monitor the space weather reports. Consult the astronomy forums. Examine the incoming data, and consider what you hope to witness. Do you hope for confirmation that our understanding of the universe is complete and that all phenomena proceed according to natural laws? Or do you hope for an unexpected discovery, an anomaly, a revelation that indicates we are not solitary beings and that the cosmos is far more peculiar than we have imagined? In either case, December 15th is approaching. The countdown has already commenced. 3 Atlas is nearing its closest approach. And somewhere in the vastness, traversing the gulf between stars, a visitor from another system is poised for its most intimate encounter with Earth. Whether that encounter is silent or speaks volumes, we are about to discover.